Hello friends and my respected teachers. Today we are going to present a presentation on the topic applications of random variables and binomial distributions. Our group name is Alpha. Myself Parag Pradeep Parab, my friend Tanveer and Hirak, we are going to present this topic. Starting with uh, random variables. Random variable. A random variable is nothing but a numerical outcome of a random phenomena. It is essentially a function that has a numerical value. Let's assume an example of a dice. If we roll a dice, then the value should be 1, 2, 3, 4, 5, 6. So this is a random variable which is assigned to that experiment. Types of random variable. There are two types of random variable. One is discrete random variable and second is continuous random variable. A discrete random variable takes on a countable number of distinct values. These values often come from a finite set of possible outcomes, like 1, 2, 3, 4. So here the set is finite. Now, in continuous random variable, it takes an infinite number of possible values. For example, a height of the students might range from 4 to 6. So this is an infinite number of possible values. So this comes under continuous random variable. Now talking about probability mass function. Let x be a discrete random variable which assumes the value x1, x2 to xn. With each value, we associate pi as p of x is equal to xi, I is equal to 1 to 3 to n. Now to satisfy probability mass function, we have to satisfy two conditions which are as follow. First is pi should be greater than 0. It means that it should be a non-negative value. Each pi value should be non-negative. The second condition is the summation of all the probabilities should be equal to 1. It means that total probability value should be equal to 1. Hence here p of xi is denoted as probability mass function of discrete random variable x. Now we will see the applications of PMF, that is probability mass function. The first application is queuing theory, which comes in PMF application. Now, the queuing theory studies how the customers of the items line up for the service, such as standing in a bank or a call center. In this context, the number of customers arriving over time is often modeled as a discrete random variable. The PMF method is used here to describe the probability of the certain number of arrivals with a specified time frame. It means at what time the customer has arrived. The real world of use is, for instance, a call center manager may use a PMF to predict the number of incoming calls every minute. So this will help him to allocate staff more effectively, ensuring minimal customer wait time. The research project example is, in research, queuing theory with PMF help to model complex traffic flow in telecommunications. For instance, in cellular network, PMF can predict the number of data packets arriving at a server. The second PMF application is genetic research. Now, talking about genetic research, first I would like to explain you in genetics, scientists often study the probability of inheriting particular traits, that how the traits are inherited from one parent to the child. Random variable here represents the presence or absence of certain traits, and PML is applied to calculate the probability. Now, how we can use it in real world is, for example, in predicting the livelihood of a child. For example, if you want to test that if there is a genetic disorder in the child from a parent, so we can use this using PMF function. Now, the result of this is that the project example I will explain is researchers normally use binomial PMF in genuine wide association studies to analyze how certain traits or disease are inherited within the population. This can help predict the spread of genetic traits in future generation. Now, my friend Tanveer will explain you about the probability density function.
Probability density function. So what do we mean by probability density function? A function f is said to be a probability density function of a continuous random variable x if it satisfies the following properties. F of x should be greater than or equal to 0 for all the values of x lying in the range of minus infinity to infinity, and f of x equal to summation of f of x dx from all the minus infinity to infinity should be equal to its summation should be equal to 1. Now, there's some real world applications of probability density function. Finance and risk analysis. So, in finance, random variables are essential in modeling continuous data such as stock prices, interest rates, or economic indicators. The probability density function represents the likelihood of a random variable falling within a specific range. It is crucial for estimating potential financial risks and returns. Some real world use of probability density function in finance and risks is as follows. For instance, in investments, analysts might use the probability density function of stock returns to assess the probability of a stock achieving a certain performance. This helps investors make informed decisions based on expected returns and associated risks. Some research project example. In risk management, research often uses probability density functions to model potential losses in a portfolio. By using continuous distributions like the normal distribution, researchers can estimate the likelihood of a significant losses under varying market conditions, allowing for a better risk mitigation strategies. So engineering and quality control. So here in engineering fields use probability density functions to model the reliability and lifespan of components, which is crucial for quality control. Here, random variables represent the time until failure of a part or system, and the probability density function describes the probability density over possible failure time. Some real world use case. Here, manufacturing companies apply probability density function analysis to predict when machinery parts might fail, which helps in optimizing the maintenance schedules and reduce unexpected breakdowns. So, some research project example. In reliability engineering research, probability density functions of failure times are used to create models that predict component lifespan under various stress conditions. This data helps in designing components that last longer and operate more reliably, especially in critical industries like aerospace. Environmental science. So, environmental scientists use probability density functions to model the distribution of pollutants or other ecological metrics over geographic areas. So, random variables in this case might represent pollutant concentration at different locations, and the probability density function shows the likelihood of specific concentration levels in certain areas. Some real world use case. For example, a probability density function can model the dispersion of air pollutants from a factory. This allows environmental agencies to estimate exposure levels across a city and takes measure to protect public health. In research project example, here research in climate science uses probability density functions to model temperature or rainfall distributions. This analysis helps in understanding the climate patterns and predicting extreme weather environments. So now my colleague Hirak will explain what is binomial distribution and its real-world application.
Binomial distribution. Definition. Binomial distribution is a discrete probability distribution which is obtained when the probability P of the happening of an event is same in all the trials and there are only two events in each trial. Calculation of binomial distribution. It is discrete probability distribution. Binomial probability is calculated by following general formula. Probability of x is equal to n combination of x into p to the power x into q to the power n minus x, where n is equal to number of trials, x is equal to number of success, p is equal to probability of success, q is equal to probability of failure, which is also count as 1 minus p. Then real world applications of binomial distribution. Medical research, clinical trials. Example, a medical study tests a new drug for treating a disease. Each patient either recovers or does not recover, which is either success and failure. After taking the drug, researchers are interested in knowing how likely it is for a certain number of patients to recover if the drug has a known effectiveness rate. Real world scenario. Suppose 100 patients take the drug and based on previous data, the drug is effective for 70% of patients. The binomial distribution helps predict how many patients are likely to recover out of the 100. For example, researchers might calculate the probability that exactly 80 patients recover. Imagine flipping a coin where heads means a patient recovers and tails means they don't. The binomial distribution helps researchers calculate the chances of getting a certain number of heads recoveries when they flip the coin for each patient in the study. And second is quality control in manufacturing defective products. Example, a factory produces thousands of smartphones every day. There is always a small chance that a product might be defective. The binomial distribution is used to estimate how many defective phones are likely to be found in a batch. Real world scenario. Suppose 5% of the phones are defective. Out of a batch of 1,000 phones, the factory uses the binomial distribution to estimate how many might be defective. If they expect 50 defective phones but 100 are found, the factory knows where there might be a bigger problem in the production line. Imagine you are checking 1,000 phones from the factory. Each phone you pick is either working or defective, which is success or failure. The binomial distribution helps predict how many defective phones you are likely to find so the factory can ensure quality. So here with this, I would like to conclude our presentation. Thank you.